Okay, so welcome to the second optional examples class on definitions, proofs and examples. And it's good to see a good turnout. So what I've done is I've extracted a selection of questions from this rather large question sheet that I've given you on full of examples on definitions, proofs and examples. But I've produced a particular I produced this extract actually as unannotated slides for you to write on if you want to for this session. So again, you don't have to hand these in, they're just for practice. The idea is that they'll reinforce various different things from the module. They're going to reinforce how to work with definitions, how to prove things, hopefully relatively routine proofs, a few ideas maybe, and of course, how do you work with examples or think up examples of your own if you're asked for them. So we're just going to do lots of that. I'll let you have some chances to think about them for a bit. You may not finish the questions in the time I give you. I'll then give you a solution to at least most of them. We'll see how we go from there. If you do finish any of the questions so quickly that you're ready to move on to the next question, feel free to do so. That's fine. Okay, so and a lot of this is about justifying your answers and the kind of justification I'm going to expect to see when I ask you to justify something. Because everything can be justified at many different levels, and so part of what you're doing in this module is getting a feel for the kind of argument I'm expecting to see when you're being asked to justify things that seem completely obvious or possibly don't seem completely obvious, depending on the question. Okay, so let's, without further ado, move on to question 1. So question 1 asks you to check a set inclusion. So I'll give you for free that you have to prove that if x is in the left-hand side, then x is also in the right-hand side. So you have to prove that x in left-hand side implies x in right-hand side. That's a typical proof structure for showing that a set is a subset of another set. But of course it's full of symbols, so you have to know what all the symbols mean. So we've got set difference. The backslash there is set difference. And the times is nothing to do with multiplications of real numbers. It's the Cartesian product. So I remind you that A times B is equal to all pairs AB, such that A is in A and B is in B. And finally, let me say that by the time you've taken the Cartesian products, you're working with subsets of R squared here. So actually, I should have vectors, because these are, you're working in R squared. So all you have to do is work with the definition of set difference and Cartesian product and this structure for proving things on the left-hand side. And I would recommend starting with let x be in the left-hand side. And I'll give you an even better hint. It's a good idea to say what the coordinates are. Then you want to make deductions from that and prove that that point is also in the right-hand side. And what I'll do is I'll let you have a few minutes to think about that while I go around and see whether people have got any idea where to start on it or whether it's routine and easy. We'll soon find out. And I'll pause the recording while you have a go at it. And you can feel free to talk amongst yourselves. Okay, so as I went around the room, I saw that some people had made more progress than others on this, and some people had got a complete proof. Let me give you my version of the proof. So we've got that x equals xy is in the left-hand side. That tells you that the first coordinate is in the first set. So the first coordinate has to be in the first set. It's a Cartesian product. So if the pair xy is on the left-hand side, it means that the first coordinate will be in the first set and the second coordinate will be in the second set. In other words, that tells you that, let's get rid of that arrow, then x is in A take away C and y is in B take away D. So that's just by definition of Cartesian product. This is optional, the bit in brackets, but it's a bit of extra additional information. Now, if x is in A take away C, then certainly x is in A, and y is certainly in B. So you are at least in A cross B. It's the first one you want. We want to show it's in A cross B, take away C cross D, so we just have to show that we're not in C cross D. So you need xy not to be in C cross D. For that, you need x is not in C or y is not in D. But actually, here we've got both. So you've actually got more information than you need. Put that in brackets as well. So you've got x is not in C and y is not in D by the above. Why is that? Well, you had that... I'll just bring that back for a second. Remember here, x is in A, take away C, so x is not in C. Y is in B, take away D, so y is not in D. So you've actually got that it's in neither C nor D, which is overkill. So certainly, xy is not in the product because both coordinates fail. You only need one of the coordinates to fail. And we finish. One could write a couple of extra lines at the end there, but we've done the main work. Does anyone have any questions on that proof? A little bit of additional exercise. What are the implications of that bit of overkill at the end there? Should it be a set equality, or is it a strict set inequality sometimes? Something for you to think about. The fact that we had overkill at the end there, we knew had too much information, suggests that it probably isn't a set equality. Maybe if you draw a few pictures, you'll convince yourself that it's usually strict. Okay. So this one is about giving examples. I'll show you both of them, both of the questions, just so you can think about both at the same time. This is give explicit examples. I've asked you to work in the real line, but obviously you can do the same thing in R squared if you want to, but in this question I said work in the real line. So, and this question too was, I can't remember, it's a past exam question, but I can't remember which year. So it was on one of the exams, this one. So find two unbounded sets so the intersection is bounded. And the second one, again working the real line. This time, find two sets in the real line, neither of which is open, but so that the union of the two is open. So anything goes, but they've got to be subsets of the real line, and they've got to have the properties you want. So it sounds pretty open-ended. How easy is it for you to just think up examples of your own that do this? So you think about both of those, and I'll come around and see how you're getting on. And again, I'll pause the recording. Okay, so I've seen that quite a lot of people have got ideas. So I thought I'd get some suggestions from the floor. Here, brief justification, by the way, is as pretty much as once you've told me what the sets are and what the intersection is correctly, you'll probably be able to say the first two sets are clearly unbounded and the last set is clearly bounded. So, but of course, sketches can reinforce that if you want them to. So I won't be doing sketches, but I'll say sketches can give extra reinforcement to your argument. So who wants to give me then two unbounded sets in the real line and what their intersection is? Or I can work out the intersection. Any suggestions?
Minus infinity to minus 2.
Minus infinity to minus 2. Is that A?
Yeah.
Okay, so do you want to include or exclude minus 2?
Include.
Include minus 2, okay. And B will be?
Minus 5 to positive infinity.
Minus 5 to positive infinity. And are you including or excluding minus 5?
Including.
Including minus 5. We excluding infinity, you have no choice because we're supposed to be working with subsets of the real line. So you must exclude infinity. Then I will attempt to work out the intersection of A with B. And I believe it goes from minus 5 up to minus 2 inclusive. And now, because we know all about intervals, I would say that A and B are clearly unbounded and that A intersection B is clearly bounded. Unbounded is what I was trying to say. And sketches are optional when you're dealing with things as straightforward as intervals. As long as you've done the calculation of the intersection correctly. Okay, any questions about that example? There are, of course, plenty of other ways to do it, and you can do it without, you don't have to use intervals, there's lots of different things you can use, but that's just one solution. Okay, the sets which are not open but whose union is open. So I'll remind you that to be not open, there must be at least one non-interior point. And that's enough. So as long as you've given sets which have obviously got some non-interior points, again, if they're intervals, then we know which intervals are open and which intervals aren't open already. So you could just quote those. But if you want, you could draw the diagrams to make it clearer. That's always a bit better justification. Just that little bit extra. Or you could say which the non-interior points are, and so on. So let's see what example people come up with. Let's have an example from maybe over from this side. Anybody got an example for me? Yes?
Could you use A from including 0 to plus infinity, and B from minus infinity to including 1?
Okay, so let's have a look. So A is going from 0 up to infinity, including 0, but of course not infinity. B is going from minus infinity up to 1. Then neither A nor B is open. And I would say that's clear because we know about intervals, but optionally, int of A, there's one non-interior point at 0, so it's not empty. And the same thing for B. But that's an optional extra. But A union B is a whole real line. And R is open. All points of the real line are interior points of the real line, got no edges, working in the real line. So that's a perfectly good example. I think that people probably got lots of other different kinds of examples. There are lots of different ways to do it, but you just must make sure that you've told me what your sets are. I want explicit ones. I don't want to see A's and B's and X's and Y's around. I want specific examples here. If I say, give me an example, then it must be an example, not infinitely many different examples. So these are really good, specific examples that I like to see. There are lots of other solutions. If you've got a solution you want to ask me about, please feel free to do it. Perhaps not now, but another time if you're not sure about your example. Okay. Here's another past exam question. This one wasn't done very well. So I'll give you some notes to try to help you avoid the mistakes that they made in the exam when this one came up. Note that F is going from R to R. So F is defined and continuous. Because it's continuous, remember, it's defined and continuous at all points of the real line. So you've got to give me, and there's lots of different ways to do this, your favourite continuous function from the real line to the real line, but it mustn't be constant. That would be too easy. So it mustn't be constant. And then any old divergent sequence of real numbers, but it's got to be one sequence, not infinitely many sequences. There mustn't be any unknowns left in there. You've got to tell me what your sequence is. I want a specific sequence. I want a specific function. The function's got to be continuous on the whole real line. It's non-constant, and it turns this divergent sequence into a convergent sequence after you apply the values. This notation here has been known to confuse people, but that's just a sequence. You'll start with a sequence x1, x2, x3, and you'll get a new sequence which is going to go f of x1, f of x2, f of x3. By the time you've applied the function, that's what this one is here. That just means use the function to convert your old sequence into a new sequence, term by term. The first sequence you mentioned had to be a divergent sequence, which means it didn't converge. Doesn't mean that just means it doesn't converge. So you're not required to make it go off to plus or minus infinity or anything like that, as long as it doesn't converge to a real number. So it can oscillate if it wants. So that I can see two clear different plans to do this. You could think of trying to do it with something oscillating, or you could think of trying to do it with something that heads off to plus or minus infinity for your sequence. And then you have to have a continuous function from R to R that fixes it and takes it from this divergent sequence into a convergent one. I can think of lots of different solutions. Let's see what you can come up with in a few minutes. Okay, some of you have got solutions, some of you have got a bit stuck, and some of you have fallen into the traps that I would say the majority of the class fell into during the exam. So there are a few issues here. Note, we're going to have to define f of x for all the numbers x, not just what f of xn is. It's not enough to define f of xn. So quite a lot of the answers in the exam just told me what they wanted f of xn to be, but I couldn't tell what the function f was. It didn't specify a function, and it usually didn't actually work, at least in any obvious way. So I'll note that f of x equals 1 over x is not valid. It's no good, because f of 0 is undefined. That was the most common error in the exam when I set this. Most people went for the function 1 over x and then took the sequence to be n, and then said 1 over n tended to 0. And that was fine as far as it went, but unfortunately 1 over x isn't a continuous function from R to R, because it's not even defined at 0. So here are two different solutions. I think I need a new page. Here we go. So solution 1, you can take xn equals minus 1 to the n, which is divergent, and f of x equals... How can you convert that divergent sequence into a convergent sequence? Has anyone got a nice continuous function that will convert minus 1 to the n? Yes? X squared minus 1, or x squared, or whatever. You want x squared minus 1 is fine. X squared minus 1. Then this is a that's non-constant. Continuous R to R. And f of xn is 0 for all n. So the sequence of values is just a constant sequence 0 which converges. Okay, so that does one way round. If you do want to use a sequence xn equals n, that's a standard divergent sequence. Now we can't use 1 over x because that's not defined at 0, but perhaps we can find a different continuous function that will do something nice to this. Did anyone come up with an example of a nice continuous function which you can apply to n and get something that converges? Yeah, what have you got?
E to the minus x.
I like that one. Good. So we'll that's a really nice continuous function from R to R. Then f of xn is e to the minus n, which tends to naught and then tends to infinity. So that's convergent. So that's the sort of thing you have to do if you're asked for an example of something. It's got to be an example. The thing that you give must be a thing of the right type. If you're asked for a continuous function from R to R, it must be a continuous function from R to R, which means it's got to be defined at all points of R, and it's got to be continuous everywhere on R, and taking real values. That's the conditions you've got to satisfy for f. The sequence you chose must be divergent in the first place, but when you apply the function, it must become convergent. So these are typical exam questions. Give an example of some things with certain combinations of properties. Come up quite often as parts of exam questions. Okay, now I won't have time to let you think about this last one. I tell you what I'll do is, I don't think I want to spoil your fun. I think we'll have an example of this in lectures later in the lectures. So see lectures. But by now you've got the idea of what you've got to do. So you can have a go at this and see if you can come up with an example. And if you're not sure about your example, you feel free to ask me. But I think we'll stop there and we'll resume at 3 o'clock for the lecture.